All right, welcome everyone. We are excited to have Victor Veitch here today. He's an assistant professor in the data science and statistics department at the University of Chicago and a research scientist at Google DeepMind. And he's done a bunch of foundational work in causal machine learning, which is how Danya and I got to know him. And he was also the main author of the causality chapter in Kevin Murphy's new probabilistic machine learning textbook. So if you've made it through the 1,000 pages, you'll get to learn about causality from Victor. As usual, we'll start with a sort of brief discussant slides, which I'll give today to kind of contextualize how this fits in what we've seen before. And then we'll switch over to Victor. Turn your cameras on if you can. And I think, Victor, you're probably happy to take questions as we go. Is that right?
Yeah, that's right. Interrupt
Okay.
me.
All right, cool. Yeah, so in the series so far, we have been looking primarily at sort of identifiable representation learning. So Johnny Sheep kicked us off last year with a nice talk that sort of said, if you take this model seriously, we have some set of latent variables and then some mixing function that maps to entangled X, then really you can think of identifiability as some combination of assumptions on the latent distribution Z and the mixing function G. And we've then seen a series of talks over the last kind of couple of months that have described different ways that we can constrain either the encoder or the decoder or the latent distribution in order to identify individual latents. And a pretty common strategy is usually something like first show linear identifiability of the latent variables and then leverage something like sparsity or independence or something to actually disentangle the individual latent variables. Today, we're going to sort of put that aside and say, and take seriously this this sort of empirical observation, or I don't know, that in practice often something like linearity shows up in the internal representations of large-scale models, and Victor's going to be far more precise about what we mean by that. But something like sort of concepts like man versus woman show up as linear directions in latent space. And so sort of in the language of the identifiability talks, we can think of these concepts as being sort of linearly identifiable. But I'm glossing over the wrinkle that they're actually far more concepts than latent dimensions. And so there isn't a notion of actually disentangling these concepts in these models. But nevertheless, I think it's a very sort of useful practical observation that these concepts show up linearly. And we want to understand that better. And with that, I'm going to hand over to Victor to explain that.
Great. Okay, so thanks very much for the invitation and the introduction. Yeah, let me just dive in. Sorry, actually, before I dive in, let me just say it is totally worth reading through the first 1,500 pages of Kevin Murphy's book to get to the chapter that Alex and I wrote. I promise you should totally do that. Okay, great. So this talk is in principle going to cover material from 2 papers with some of my students and postdocs that I've worked with. In the interest of time, I won't list them all, but they are all phenomenal. So highly recommend talking to any of them if you ever get a chance to meet them. Okay, so let me start at a very high level, which I think is relevant for this talk, but also relevant for kind of what we're doing in causal representation learning generally. With this observation that in like maybe the last, I don't know, 4 or 5 years, there's been a sort of real vibe shift in machine learning, right? Where I'd say before that time, we were in a situation where nothing quite worked and all of our effort was going into trying to build, more elaborate systems that would actually like do the things that we wanted to do, right? And the thing which has happened more recently is, in fact, now we have built some systems which work amazingly well, but we don't really understand why, right? And so what I mean by that is like, the complex behavior of generative AI systems. So here I'm mostly talking about large language models, is an emergent phenomena that comes up from doing like a very dumb proxy task, right? So in particular, in the case of LLMs, almost all of the work is done by just training a model to predict what is the next word from, from like a sequence of words, right? And so it's just a next word prediction task, right? But the behavior that we actually care about, right, is behavior which is like, can I write Python code which compiles? Can I solve hard math problems? Can I accurately answer trivia problems or whatever, right? So like the point is there's this significant gap between the part of the system that we designed, which is just like the simple proxy thing, and the behavior that we actually care about, which is some kind of complex emergent consequence of the proxy objective that we're using. Right. And this is quite different, I think, than like machine learning 5 years ago, where it's like really we were designing things, specifically aimed at the goals that we were actually trying to accomplish. Okay. And so this shift creates really some like fundamental problems, right? Or like it does really change the nature of what we're doing, right? So an obvious one is, well, just like what are the limitations of these systems or of these approaches, right? Like, will it be the case that GPT-5 or GPT-6 or whatever Gemini Super Ultra is genuinely strong artificial intelligence, right? Like, can you articulate a specific task that a human can do that you are confident that we will not be able to make an LLM do just by training on more and more data, right? So I personally cannot confidently answer that question, right? But like a lot of that like lack of confidence is because we just don't have any like really deep understanding of what these systems are or how they work, right? A very closely related question is, when can we trust these systems, right? So if you want to like go and put large language models into deployment, right, when are they going to behave in the way that you want them to behave, right? That's sort of like the very concrete version of this. A stronger version of this is, if we're actually going to build something that looks like genuinely like artificial general intelligence, right, how do we make sure that that ends up going well, right? So because it just does seem at the moment like, in fact, it's much easier to build powerful systems than it is to understand them. Okay, and so I think like in consequence of like this phenomena and these problems, there is sort of a new kind of thing happening in machine learning. I want to pitch you on like we should take seriously this idea that what we need is a science of generative artificial intelligence, right? So this is like theoretical machine learning in the sense of where theoretical is used in the sense of theoretical physics, right? Like we have a physical system, it exists in the world, right? And we want to develop like a deeper, more precise understanding of the system in order to answer like fundamental questions about its behavior, right? It's shifted from being something that feels like engineering to something that feels like science, right? And so the overall motivation is like, we're going to try and take this seriously. Okay, so what does that actually look like, right? So what might it look like to try and develop a science of generative AI? So in this talk, I'm going to pick like a sort of like the simplest version of this, right? So like one step up the mountain, and use that as a way of trying to make this idea concrete. Okay, so just for context, right? Generally, we're going to be looking at text-controlled generative models, right? And so the structure that these things all have is that we have some input text X, typically like a sentence or like some sequence of words, right? And we're going to map that to a vector representation, typically which is like real vectors in some finite dimensional space. Okay, and then the structure of these models that we sample some output Y, next word, next sentence, whatever, right, from a distribution defined by this representation vector. Okay, and our goal here, the sort of intermediate goal, right, is going to be understanding how semantic structure is encoded in the algebraic structure of this representation vector, right? And so by semantic structure, I mean things like in the context of a large language model, will the output be in English and French? Will it be in present tense or past tense? Is it about a man or about a woman? Questions like this, right? High level concepts. Right, in text to image, which I unfortunately realistically probably won't get to, but the question was, would the output be a photo or a painting? Would it be a dog or an astronaut? Right, so like variables that are semantically meaningful to humans, right? These somehow are encoded in the algebraic structure of the representations. How does that encoding happen, right? So what is actually going on there, right? So that's the intermediate goal. right? And what we're going to do is narrow that even further in this talk to the really specific task of understanding this idea, the so-called linear representation hypothesis, right? Where informally, the linear representation hypothesis is the idea that high-level concepts are encoded linearly in the representation space of the model, right? So this is a thing which exists in sort of the zeitgeist of LLM interpretability land. And I will in a second, try and say more precisely what this means, right? But the point is, there is some empirically observed phenomena where for some notion of linear, what we find often is that we have linear representations. Okay. Okay, so the problems that we're getting interested in here. So the first one is, what does linear even mean, right? So informal statements are very common. There's empirical evidence. I haven't told you what it is yet, but like overall, it's quite hard to just find a definition in this literature, and so we're going to make an effort to give a definition, right? The second question is about this phenomena where very often, you can do things like cosine similarity between embedding vectors in order to capture like semantic closeness, right? So for example, king minus queen is approximately parallel to man minus woman, right? There's a question here, which is, well, why would like Euclidean geometry on the embedding space have anything to do with like human intuitions about semantics, right? So where does that structure come from? And then the third question, which we honestly will not get to, is, if this linear structure does exist, where does it come from, right? So is this actually something like fundamental, or is it about like, model architecture, training objectives, or something else, right? Like why do we have this kind of like linear identifiability emerging? Okay, so let's jump into these first two questions. Okay, so what does linear even mean? I said like this linear representation hypothesis is a thing that has been discussed in the literature. And in fact, there are at least 3 different ideas of what it means to have a linear representation, right? A linear representation of a concept. So the first one, which is the most famous, is this like word-to-vec parallel subspace notion, right? And so the idea here is if we have a concept, which is the concept of sex, right? And we have pairs of words that express that concept. So woman and man, queen and king, which differ only by the value of this concept, right? Then there's this idea that perhaps the difference in the embedding of man minus the embedding of woman will be parallel to the embedding of king minus the embedding of queen, right? So it's like a vector parallelization thing, right? So this is a very famous word-to-vec results. That's one notion of linearity. Right. A second notion of linearity is that if you take the internal representations of language models, right, and then try to train a classifier to predict whether the output will be in French or in English, right, exhibit some value of a concept, then it turns out that very often it suffices to train just simple logistic regression, right? And so the sense in which you have a linear representation here is that, of course, you can predict the value of the output, the value of like some output concept from the representation, right? We know the representation vector contains that information, right? But in principle, you might expect that you would need to train some like very complicated classifier in order to extract the information from that representation, right? And the empirical observation here is that, in fact, you generally don't need to train like a deep neural network or whatever, right? Just simple logistic regression often suffices basically perfectly, right? And so the claim is that if I take an LLM representation and I want to predict some property of the output, right, I can do it with just a linear model, right? Which is a highly non-trivial empirical observation because of the linearity. The final notion that has come up in the literature is this steering vector notion, right? Which is the idea that, well, if I map some input string to a representation vector, right, such that the next word would be, say, king, then there exists some vector encoding the sex concept, like a male to female concept, where if I just add a multiple of the steering vector to my representation, I can change the target concept corresponding to that vector in isolation, right? So there is some male to female vector, right? Where by adding on a multiple of that thing, I will be able to change the output from king to queen or man to woman or whatever, right? Like I can manipulate the concept that gets expressed by adding a vector, a suitably chosen vector in the representation space, right? So this is the intervention or steering vector notion of linear representation. Okay, so all three of these things have been discussed in the literature. And the problem that we're going to be interested in for now is, well, it's not clear how these three notions of linear representation relate to each other, right? Nor which is like the right notion of linearity, right? The one that we might say use as a foundation for LLM interpretability, right? So this is the problem we're going to be interested in. Okay, and so the basic strategy here, or the basic problem we have, is understand how these things relate to each other, right? And our strategy for achieving understanding here is going to go as follows. So first, we're going to define what concept, high-level concept means using causal language, right? So we need some kind of mathematical formalism that's going to allow us to like reason about the relationships between these things, right? Once we have such a formalism, we're going to give a precise definition of the subspace notion of linearity, right? And then once we have that in place, we're going to prove connections between the subspace notion of linearity and the other notions of linearity, right? So that's the basic flow of the approach here. Okay, so here is some extremely simple background on language models. So this is the only structure we need, right? We're going to view a language model as a thing which maps any input sentence X, right, to a vector in a d-dimensional real space, right? We are also going to view a language model as a thing which has some fixed finite size vocabulary, right? So this is like a large collection of words, right? And what we're going to do is take each word and map it to a vector in the same d-dimensional space, right? So the transformer stack produces this embedding. So these unembedding vectors, which correspond to words in the vocabulary, are just fixed vectors that were learned during model training, right? And then the procedure that we're going to use to select the next word Y, conditional on the context sentence X, right, is just sample from the softmax distribution defined by this expression. Okay, so it's just softmax sampling, and that's it. That's the only background that we're going to need, the only structure about language models that we need to use. Okay, right. So we said the first step is define what it means to have a concept in language models. And so we're going to specialize a little bit, we're going to specialize a little bit and take the following view, which is we're going to imagine that the generative process for the language model looks something like this, right? So we specify some context string X, right? That context string now defines some distribution over high-level concepts, right? So if we have a sentence like "he is the," right, then it's very likely that the output is male, right? It's also very likely that the output is in English, right? So these are things that, like, these are high-level semantically interpretable concepts which were influenced or set by the value of the context string, right? Okay, now given these concept values, what we're going to do is sample the next word conditional on these things, right? And so the next word might be king or queen or roi or rien. These are French for king and queen, respectively. Okay, and so this is the generative process that we're going to use abstractly for the language model. Okay, with this generative process in mind, we're going to say that we are going to define a binary concept W as anything where there is a counterfactual set of words that differ exactly on that concept, right? So this is not the most general possible notion, but it's at least a precise notion, right, which we can work with. And so, like, for example, we can define the concept of man or male to female, man to woman, right, by this counterfactual pair, which is the words man, woman, the words king, queen, the words uncle, aunt, and so forth, right? So it's just like a concept is anything where I can give you a counterfactual pair of words which exhibits that. Okay, we're also going to need the idea, another idea very shortly, which is this idea of causal separability, right? Which is to say a pair of binary concepts we're going to call causally separable if all counterfactual tuples, right, are defined for each possible value of both W and Z. Okay, so that's kind of a mouthful, right? But what this is supposed to capture is the idea of concepts that can be manipulated in isolation, right? So I can change whether the output is a man or a woman freely of whether or not the output is in English or in French, right? And so if you just meditate on that desiderata, right, like what does it mean for me to be able to change two concepts freely, right? You will eventually convince yourself that a reasonable formalization of that is just to say, well, all of the counterfactuals are well defined for each pair of possible values. Okay, so now that we have this in place, we can start mathematizing this linear representation problem, right? So how are we going to do that, right? Well, right. So the very first observation here, right, is that there are in fact two representation spaces at work in the language model, right? So that there's the representation space belonging to the word unembedding vectors, right? And there is the representation space that belongs to the context sentence embedding vectors, right? And so we actually need a notion of linear representation, right, that belongs in each of these spaces, right? So we actually need two notions of subspace, one for each of these two distinct representation spaces. Okay. At the very least, we have to commit to one or the other, but we're going to give one for each. Okay, and so in the word case, it's relatively straightforward, right? What we're going to do is say, well, let W be a concept, right, which is defined by a counterfactual pair y1 and y0, right? And then we'll just say, okay, the vector gamma bar W, right, is a subspace representation of the concept W, right? If the difference in the representations of any counterfactual pair is parallel to gamma bar W. Okay, so this is exactly the king minus queen is parallel to man minus woman, right? There is just a fixed vector, which is gamma bar male to female, right? Where all these differences are going to be parallel, right? So we're going to take all counterfactuals that differ just on the concept. The difference in embeddings has to be parallel. Okay, the analogous thing intuitively in the embedding space is to say, consider counterfactual pairs of sentences, right? So sentences that differ only on one concept, right? So he is the, she is the, right? And then again require that all sentences which are counterfactual pairs on just that concept are parallel to a single fixed vector. Okay? So I'm being a little bit sloppy about what it means to have a counterfactual pair of sentences. So let me just give a precise definition of this. I'm going to mostly skim over this because it's a little bit involved, right? In the unembedding case, it was literally counterfactuals. It's about outputs, right? In the embedding case, it's actually that each context string X defines a probability distribution over concept values, right? And so the thing that has to happen here, right, is saying, well, a pair of embedding representations corresponding to two sentences is like a counterfactual pair, right? If we have this condition, right? So it changes the probability of like, is this about a man? Is this about a woman? Right? So that's W, but it doesn't change any off-target concept, right? So it does not change whether this is in English or in French, right? So I'm just gonna blitz by this, but again, it is just kind of like, you know, what would it mean to have a pair of sentences which change it where like they differ in exactly one concept? This is just the natural formalization of that. Okay, and so the first result here, so now we have a mathematical formalism, right? And we have a precise definition of this subspace representation, right? And so the first pair of results here is first that if we have an unembedding representation vector, gamma bar W, right, which we constructed from counterfactual pairs of words, right, expressing the concept W, then this vector, gamma bar W, will be a logit linear predictor for the value of the concept W. Okay, and so the statement here is like I take pairs like you know, man minus woman, uncle minus aunt, king minus queen, and so forth, right? I get all those differences. I construct a vector by averaging those differences, right? Now what I can do is take some free-form text, right? Do a forward pass through a large language model, right? And produce an embedding vector lambda, right? And if I now want to predict whether the output of lambda will be about a man or a woman, right, I can use the vector that I constructed from counterfactual word pairs as a logit linear predictor, right, of the value of that concept, right? And so the point here is like I'm tying together this subspace notion and this probing notion, right? This unifies the two things, right, in a way which is not trivial, right? Like those two things did not have to align in this way, right? And the fact that they do is ultimately a consequence of like the softmax structure, like the softmax link function, which I'll talk very briefly about in just a second. Okay, the other result is that if I construct this embedding representation, this lambda bar w, so this is a thing I can construct from counterfactual pairs of sentences, right? Then this lambda bar w will act as a steering vector, right? Or act as this intervention notion, right? Which is to say, if I, take some free-form text, right, and I produce the representation vector of that, and I want to just change some concept in isolation, I want to make the output French, right? What I can do is just add on some suitably chosen multiple of this lambda bar w, and that will allow me to change the target concept in isolation, right? And so the point here is like I construct things via counterfactual pairs, right? And then the theorem says that if I construct via counterfactual pairs of words, that gives me the ability to measure the value of a concept. And if I construct via counterfactual pairs of sentences, that gives me the ability to intervene on the value of a concept, right? So I've now connected the subspace notion to the measurement and intervention notions.
In these sort of empirical steering vector works, is this exactly how they compute the steering vector, or do they have some other mechanism for doing that?
So morally, it's this. In practice, it's a little bit like they futz around a little bit more. But like say the version of this which is cleanest, right, is you and say like what we did in the concept algebra paper, right? It's that you do construct two sentences, right, which differ exactly on some concepts. So like he is the king, she is the queen, right? You construct many such pairs of sentences, right? And then you just average the difference of the representations of those pairs, right? And in the language model context, there's some like denoising operations that go on, which seem to help empirically. So everything's like slightly complicated empirically, because like if we think about the word queen, right? Queen is like female monarch and chess piece and British rock band, at least, right? And so there is some like complication about what happens, but yeah, like morally speaking, these actual differences of sentences is a thing that works basically in this way to construct these steering vectors. Okay, so let me just, to make this like a little bit more mysterious, sketch the simplest version of this proof, right? So this is a theorem that says, let W be a concept. So is this in English or French? Is the output English-French? Is the output about a man or a woman? And let gamma bar W be the subspace unembedding representation, right? So that's the thing I constructed from counterfactual pairs of words, right? Then the theorem is that the logit probability that W is equal to 1, so this is about a man, right, is equal to this like just linear product. Is it basically equal to like the logit, like the linear logit predictor, where the regression vector is the subspace unembedding representation, right? So the point is like the thing I would have gotten by training linear regression is also exactly the same vector I get by averaging these counterfactual pairs, right? That's the meaning of this theorem statement. Okay, and so the point here, the point of showing this is that it's kind of extremely straightforward, right? So what do you do? Well, let's just say probability that it's man condition, probably the next word is man, given that the next word is either man or woman, and lambda, right, is just equal to this thing, right? So this is just writing out the conditional probability, or this is writing out the definition of the logit, right? Having written out the definition of the logit, we now just sub in the softmax, right, which involves an exponential, right? So we have a ratio of exponentials. The ratio of exponentials, yeah, right. So it's like lambda. So the numerator is lambda transpose gamma of y1. The denominator is, x of lambda transpose gamma of y0, right? So we just plug in the softmax. We have a ratio of exponentials. That ratio moves to a difference of the numerators, right? And then the log kills the exponential, right? And so the point is like basically as soon as you have a definition of what it means to have a concept in this causal language, right, then just plugging things into the softmax immediately gives you this connection between the subspace notion and the linear probing notion, right? And so the softmax is playing a really critical role here, right? If you use some other link function, this theorem wouldn't be true, right? But once you have the softmax structure, you can now see that everything follows from that. Okay, let me skip this slide in the interest of time. Okay, so let me just say where we're at so far, right? So we said, look, there are at least 3 distinct notions of linearity that have come up in the literature and which seem like sensible, right? There's this subspace notion, right? There's a measurement or probing notion, right? And there's an intervention notion. Okay, so what did we do? We said, well, let's introduce some causal language and formalize the subspace notion, right? And the first observation here was actually we need 2 notions of subspace, right? One in the embedding space and one in the unembedding space, right? That was the first observation. Okay, and the thing that we've gotten here, or that we've gotten to so far, is that this unembedding subspace representation maps to measurement, right? And this embedding representation maps to intervention, right? So we have a partial unification of these ideas of linearity, right? Where that partial unification is just following from softmax structure, right? But we have not said anything at this point about how the embedding and unembedding representations relate to each other, right? So we have like unembedding goes to measurement, embedding goes to intervention, but we haven't said anything about how embeddings and unembeddings connect. Okay, there's also another question that we haven't said anything about yet, which turns out to be extremely closely related, right? Which is, well, what, if any, is the right notion of inner product on this representation space, right? So this is the question of like, you know, what geometry would actually correspond to like semantics as understood by humans, right? So these 2 things will turn out to be very closely related. Okay, so maybe this is like my neuroticism forces me to have this bit, but plug your ears if it will confuse you. Okay, so so a complication which I've just sort of ignored in this unembedding space, right? Because of the nature of softmax, if you take the unembeddings and add some constant vector to them, none of the probabilities change, right? So the space that the unembeddings naturally live in, right, is an affine space, not a vector space, right? Okay, so what we need to do is move to a vector space by defining the space of differences between unembedding vectors, right? So this is just going to make 0 a meaningful notion, right? Having done that, the thing that we're going to be interested in doing is looking at this new unembedding space and putting an inner product on that thing, right? So that's the structure we're going to be interested in studying, an inner product on the space of differences of unembedding vectors. Okay, so that would be like cosine, the thing that's going to allow us to find cosine similarity of king minus queen versus man minus woman, right? Okay, now the other thing that I've been a bit fast and loose about is that this unembedding notion is only about like parallel, right? So this representation gamma bar W has a direction, but no notion of magnitude, right? But now we want to actually talk about vectors, right? And so what we're going to do is say, well, once we have an inner product on this space, we're just going to take the canonical representation of the direction to be the vector with magnitude 1. Right? Okay, so the point is now we actually have a proper vector space, and we're going to talk about vectors, and what we're interested in doing is reasoning about the inner product on that vector space. Okay, so this is just bookkeeping. Now please unplug your ears, and we will return to conceptually meaningful points. Okay, right. So the problem that we're going to be interested in here is what should this inner product be, right? And you might think, oh, there's no problem here at all. What this inner product should be is the Euclidean inner product, because everything we ever do is the Euclidean inner product, right? And so it seems quite natural to just like throw that in and not even think about it. And in fact, I'd say like the #1 point of confusion in this literature has been people just using the Euclidean inner product willy-nilly without really thinking about whether or not that is a sensible thing to do. Okay, so there is a problem with Euclidean inner product. Let me say what it is. So the first thing is this observation that the softmax probability distribution is invariant to linear transformations, right? So this is probably familiar to anybody who's looked at causal representation learning before, right? But the point here is I can take some invertible matrix A, apply it to all of my unembedding vectors, right? Apply the transpose inverse to all of my embedding vectors, right? And then this function here doesn't change, right? But the reason this is an issue is that when I train the large language model, right, the embeddings only influence the loss function through this softmax, right? And so at best, I can only hope to identify these embedding vectors, right? These embedding and unembedding vectors up to some invertible linear transformation, right? Like in principle, the particular linear transformation is just like set by the random seed used to initialize the model or whatever, right? Like it's not a thing identified by the training objective. Okay, the problem that we have here, right, is that the inner product on this gamma space is not invariant to this linear transformation, right? And so ultimately what happens is like, you know, Euclidean distance or like whatever, you like cosine inner product or whatever out of the box, right, just on like the unembeddings in the language model, right, is ultimately a thing which depends on like the random initialization of the model, right? It doesn't have any fundamental status. It wasn't picked out by the training, right? It seems a priori there's like no particular reason to prefer Euclidean geometry to any other inner product geometry, right? So this is the problem that we have. Okay, so in particular, what that means is that if it is possible to encode semantics geometrically, right? So things like cosine similarity are actually going to encode semantic structure. We need some sort of additional principle for picking out a privileged inner product, right? An inner product that will do the right thing. Right, okay, so the particular desiderata that we're going to appeal to here, right, is the following notion where we say an inner product on this space is a causal inner product, right, if the representation of any two causally separable concepts are orthogonal. Right, so this means if I have two things that I can manipulate freely, right, like French versus English and man versus woman, right, then to encode that geometrically, I'm going to ask for the representations of those concepts to be orthogonal, right? And so I think that's like a pretty intuitive desiderata, right, for like encoding semantics into meaning, right? Things that can be independently manipulated are orthogonal. Right, it turns out that even beyond being like intuitively desirable, this causal inner product notion has like an immediate, very desirable property, which is that if you have a causal inner product, then it will have the special property that under the causal inner product, the embedding representation of a concept W is the Riesz representer, right, of the unembedding representation of the same concept. Okay, so this is kind of a mouthful. So let me say what this would mean is if the Euclidean inner product was a causal inner product, right, then what this would tell me is that I could get to the embedding representation by taking the transpose of the unembedding representation, right? So it's just the unembeddings are row vectors, the embeddings are column vectors. I want to know how to pass from row vectors to column vectors, right? If Euclidean was the right thing, I could take the transpose. Euclidean in general is not the right thing, right? But if I take a causal inner product, then this generalization of the transpose operation becomes the right thing, right? Okay, and so pictorially what's happening, right, is that in general, if I have concepts like male to female and English to French, right, I actually have two distinct representations for each of those concepts, right? I have the unembedding representation, which is about words, and the embedding representation, which is about sentences, right? And just in the default representation space, these are totally distinct entities. However, if I apply some linear transformation, which makes the Euclidean inner product a causal inner product, right? So I apply some linear transformation to all of my embeddings, right? What now happens is that these things unify exactly, right? So the embedding representation and the unembedding representation become the same entity, right? Related just by transpose in the way that is like familiar from ordinary geometry. Okay, and so the point is we started with this like intuitive condition that causally separable concepts should have orthogonal representations, right? And then we have a theorem that says, well, if you have that condition, then every notion of linear representation unifies. Okay, so this is the key thing. Okay, so a problem that still remains here is that the causal inner product is a thing which is defined very abstractly, right? And so, you know, if you actually want to do something with that causal inner product, you're in some trouble, right? Or like you at least know, you'd like to know how to find it. Okay, and so a question here is, well, what can you actually do? And it turns out that, and maybe in the interest of time, I won't say too much about why this is the case, but under some like fairly plausible causal assumptions, it turns out that you can identify this causal inner product in the following way, right? Which is that the causal inner product between two unembedding vectors is equal to applying this inverse covariance of the unembedding matrix operation in between these two things, right? And the flavor of the assumption that goes into this, right, is that if you randomly sample words from the dictionary, right, concepts that are causally separable will also be statistically independent, right? And so this is like the flavor of assumption that we always use for causal identifiability, right? Like you know, to get identification, you always have to say something about how does causal structure relate to independent structure, which is the thing that you can measure, right? And the idea is like, well, words in the dictionary. So like if it's just like words found in the wild, right, there can be strong correlations, right? Like maybe French writing is much more about men than English writing is, right? And so the fact that they're causally separable doesn't mean they're statistically independent, right? Whereas if you just sample words at random from the vocabulary, there is one English word which means male king, or sorry, you know, male monarch, right? And there is one French word that means male monarch, right? And so irrespective of the actual quirks of history, right, that said, oh, there were way more like French kings than like English kings or whatever. I don't know if that's true, but like whatever the quirk of history, right, the nature of just like how words are constructed means that causally separable concepts should have statistical independency. So that's the assumption that is underlying this. And then it's relatively straightforward to establish that this is a causal inner product under that assumption. Okay, so that's the structure that is happening here. Okay, so we have now completed the theory, where basically the upshot is under a suitable notion of inner product, we have unified all notions of linear representation. Okay, so let's look at some experiments, right? These are all going to be on Llama 2 7b, right? The basic structure of these experiments are we're going to define concepts by counterfactual pairs of words, right? So the concept English to French by king, roi, queen, rien, etc. Right? And we're going to look at 27 concepts, 23 of which are from the big analogy test set, which is the thing that was constructed by other people in like the Word2Vec era, and 4 of which are about language pairs. Okay, and so the very first question that we'd like to answer here is, well, do linear representations of concepts actually exist in large language models? Right, and so the structure of the experiment, which we use to look at that, is to say take a concept, in this case, the country to capital concept, right, which is exhibited by pairs like Paris, France, Tokyo, Japan, Cairo, Egypt, right? Then what we're going to do is take all but one pair, right, compute the average of that leave one out thing as an estimate of the direction associated with this concept, right? And then look at the inner product, the causal inner product, the causal inner product between that estimate of the direction, right, and the direction of the remaining pair, right? So we're going to look at, say, Paris minus France versus country to capital, right? And so if we actually have a linear representation, what we should expect is a strongly right-skewed distribution in these inner products, right? Because all of these, this is just measuring, like we're basically projecting Paris minus France onto the country capital direction, right? Paris is the capital of France. We should see this right skewed structure, right? These blue curves are just random pairs of words, right? And so what we see is like if you just take a random pair of words, it's approximately 0, right? But if you take things that actually exhibit the concept, this inner product is large. Causal inner product is large. Okay, and so for 26 of the 27 concepts, we find strong evidence of this linear structure indeed existing. Okay, the second question that we'd like to address is whether or not the causal inner product actually succeeds in encoding semantics, right? And so what's plotted on this heat map is the absolute value of the cosine similarity as measured by the causal inner product between all of these concepts. Okay, the thing that you should observe here, right, is this like block diagonal structure, right? Where if you look at this for a while, you will convince yourself that the block diagonal structure is encoding something like semantics, right? So this upper block all relates to verb suffixes, right? This middle block is about tense, I think. The block at the bottom here is about what language you're speaking, right? And so forth. Okay, and so remember that our claim here was that the causal inner product should have any causally separable concept as orthogonal, right? And so we do indeed see most things are orthogonal, right? And the places where orthogonality fails, it is actually things that cannot be freely manipulated from each other, right? Like, you know, the English to German and English to French concepts are not freely manipulable, right? So this is the structure that we're seeing here. It's also worth noting that you know, if you really stare at this thing carefully, it in fact like makes a surprising amount of sense. So maybe I'll just point out one. So concept 19 is whether the output will be lowercase or uppercase. So it's about capitalization, right? So if we look at the inner product between concept 19 and these language values, right, we see that there's non-trivial inner product for every language pair except French to Spanish, where it's like orthogonal, right? So it's like we have orthogonality here and non-orthogonality everywhere else. And the interesting thing about this is French and Spanish have the same capitalization conventions, but every other language pair has a different capitalization convention. So like the rules of capitalization are different between English and German, English and French and German, and so forth. Right, and so what we see is that the linear structure appears to like just capture this phenomena, right, where you can do free manipulation of French to Spanish versus upper lowercase, but not English to German versus upper lowercase. Okay, now you might say, okay, great, the causal inner product does seem to capture semantics, but maybe every inner product captures semantics, right? So here's a randomly chosen inner product, right, where we see the semantics are like totally wrong. Right. A more interesting phenomena is that here's the default Euclidean inner product, the naive thing, right? And a thing that we see is that it looks much better than chance, right? Now, it's actually far from perfect. So if you look at the differences, and maybe I won't go through this exercise, but like, for example, this concept here, which is about word frequency in the Euclidean inner product, has like high inner product with many other unrelated things. But in the causal inner product, it doesn't have this phenomena. So in fact, the semantics of the causal inner product do in fact make more sense, right? So the Euclidean isn't perfect, but it's surprisingly better than chance. And we don't know what causes this phenomena, right? But an interesting data point, which I don't have a slide for, but which I'll note, is that we tried the same experiment with Gemma, which is like Google's open source language model. And in Gemma, you don't have this orthogonal structure in Euclidean, right? So just from like the identifiability argument, we would expect Euclidean not to be meaningful, right? In the Gemma model, Euclidean is not meaningful at all. It has no semantics, right? There is a mystery, which is somehow in Llama 2, Euclidean does have some semantic meaning, right? But it's like totally unclear why that is actually. So open problem. Okay, so a couple more experiments in the remaining thing, right? So one of our theorems was that if we constructed this unembedding vector gamma bar w, right, it would we could use that as a logit linear probe to predict the value of a concept, And so what we're going to do here is look at pairs of English and French words, right? So construct the English versus French unembedding representation of the concept. Then we're going to draw random chunks of text from either from either French Wikipedia or Spanish Wikipedia, right? And then compute this inner product thing. I mean, it's not an inner product, but I don't have a better whatever. We're going to compute the value of this map, right? And then see whether or not, in fact, this thing acts as a linear probe, right? And indeed, what we see is that this like French versus Spanish unembedding vector, right, is in fact a very strong classifier for whether you are English or whether you are Spanish or French Wikipedia, right? And that's not a generic phenomenon. Like it's not just that French and Spanish are well separated, right? If we choose a different projection, right, say the male to female direction, we see that there's perfect overlap, right? And so indeed, it's the case that as predicted, the unembedding vector will act as a linear probe for the value of the concept. Okay, the other thing, right, was this idea that the embedding vector notion, right, would allow us to do intervention or manipulation of concepts, right? And so the thing that we're going to do here is say, okay, well, let's construct the steering vector associated with concept W, right? So in principle, you can do that by creating counterfactual pairs of sentences, right? And then averaging the differences of a large number of counterfactual pairs of sentences. In practice, for many concepts, it's actually extremely difficult, right? If you just write an English sentence and a French sentence, right, those two things, like, you know, will end up differing by more than just English and French, right? There are other like implications of like changing that variable, right? But we actually have something further, right? Which is because of this like Reese representer result, right? We know that we can construct the embedding representation of a concept W, right, by constructing the unembedding representation and then applying this like whitening operation to it, right? So that was like one of our theorems. And so what we're going to do is construct these embedding vectors, right, and then try to manipulate concepts, right? And so the structure of this experiment is we start off with sentences like long live the blank, right? So the most probable next word for long live the blank is king, right? And so what we try to do here is take this vector lambda and then add on some multiple of the male to female concept vector, right? And now what we're looking at here on the y-axis is the relative probability of capital king to lowercase king, right? And on the x-axis, the relative probability of the next word being queen versus the next word being king, right? And what we see is when we add on this male to female steering vector, queen becomes much more probable, right, without changing the probability of capitalization. When we add on this uppercase to lowercase vector, right, the uppercase thing becomes much more probable, but without changing the gender of the output, right? And when we add on a French to Spanish vector, we see that we change neither the gender nor the capitalization of the output, right? And so indeed, like we are able to manipulate concepts in isolation by doing this. So Danya, do you have a question, or are you telling me I'm out of time?
I have a question. Just a quick clarification question. So here the covariance matrix would be indeed estimated from those randomly sampled words out of a dictionary, right?
Yeah, but I mean, in practice, we just take the entire vocabulary, right, and run PCA on it, right? So okay. you have like a dimension of the space by dimension of vocabulary, right? And then, you know, you compute the covariance and weight in that thing.
Great.
Yeah.
Thanks.
Cool. Okay, great. So I have 3 minutes left. So as predicted, I'm not going to go through the second paper. I have never made it to this part of the talk, but that's fine. Let me just give a teaser, right? Which is, you know, we now have unified all of these notions of linear structure, right? And seen empirically that like they really do all occur in language models. But we haven't said anything yet about like, why does that even happen in the first place, right? Like it's there, but where is it coming from? And so if you're interested, I encourage you to read this concept algebra paper, which gives at least a partial answer to where does the structure come from in the first place. And the punchline is that it's really fundamentally about the structure of probability theory and not anything to do with like model architecture or transformers or yada, yada, yada. Right? It was like a thing that was always like in some sense inevitably going to happen, just because of how probability theory is. Okay, so let me skip all of this. Da 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 da. Oh yeah, well maybe I'll just show some pictures. Right, and so similar to how we manipulated the next word, it turns out with a suitable notion of representation and like so forth, you can again do algebraic manipulations to manipulate the concepts expressed by stable diffusion. And so the thing that we're doing here is not really even saying what the representation space is, but you can change, say, the style of outputs, creating counterfactual pairs by projecting out a style dimension and adding in some other style, right? Similarly, take the same things. You can change the sex of the person output by projecting out a sex dimension and adding in some sex, right? And so the overall point here, and please do look at the paper, but the overall point is that this like algebraic manipulation of concepts, like via just like linear operations, is like generically a thing which generically is doable and exists. Okay, good. So wrapping up with 1 minute left. So linear representation we now see is actually well defined in the context of large language models, right? Where the two key ingredients are like the softmax link function is doing a lot of heavy lifting, and you need to get the right notion of inner product. So using a causal inner product is actually key in order to unify all of these notions. A higher level point is that causal language is actually extremely useful here for formalizing and reasoning about how semantics are encoded in algebraic structure. Again, the causal inner product gives a sensible geometry, right? So that this is like some like sort of key thing in interpretability, right? And this thing that I skipped, which is that the embedding notion of subspace extends to more general things, even beyond language models, via some Stein score argument. Okay, yeah, and then some open problems. So let me skip the first one because it relates to the part of the talk I didn't get to. But the second open problem, here I defined concept as a thing which was defined by a counterfactual pair of outputs, right? But like, what do we do about higher level concepts that aren't naturally encoded in such a way, right? So like, is the output truthful? Is the output positive or negative sentiment? How should you find the representations of these things? How should you reason about them, right? It's still kind of open. Another question, which I think is quite interesting, is like, how do all of these like linear notions connect to like, so let's say like sparsity notions or VAE notions of the kind that are like more commonly studied in causal representation learning. And then there's also like an ongoing thing in the background where also in the context of LLM interpretability, people have become very interested in this sparse VAE structure. And so like understanding the connection there seems key. Okay, sorry, I'm 1 minute over, so I'll stop here, and thank you very much.
Thanks, Victor. That was great.
Thanks. Yeah, that's very interesting that Gemma fails, or not fails rather. But from my understanding, the fact that the llama Euclidean dot products look similar to the like causal product dot products means that things are kind of uncorrelated in the llama space in a way that we would want, like, gender being decorrelated from language and so on. Like, you only need to do like a little bit of reweighting of stuff to kind of get that more crisp independent structure that you see. So for some reason, these other large language models, even though they're performant, things seem like much more entangled. Is that the right way to view that?
Yeah, so I think that is the right takeaway. But the surprise is in the other direction, right? Because like there's absolutely nothing in the training objective, right, which privileges Euclidean, right? And so like a priori, we should expect the Euclidean inner product to look just like a randomly chosen inner product. Yeah. Right. And so
I don't. That's not what I understand. So can I just try to see where I'm confused here? So the fact that your causal inner product is defined by this correlation matrix, doesn't this suggest that if that is, things are already decorrelated, then the Euclidean is fine? Or is that the wrong implication that I'm getting at there?
Well, no, sorry. So, but it's a correlation of the embedding vectors, right? But there's nothing in the training objective which like cares at all about correlation of the embedding vectors as such. Right. So it's just like there's like you never see like a gamma interaction ever, right, in training, right? And so there's like sort of no actual pressure on that thing to like behave in any particular way. Right. I mean, this is just a phenomenon that like you only have like identifiability up to invertible linear transformation, right? And so if I like take a whitened covariance matrix and then make things like arbitrarily non-whitened covariance, right? Like my objective function has not changed at all.
Maybe if I could check my
Yeah.
like the way that I interpreted it, and I agree with you that it's surprising Llama had any sort of base axis alignment at all. And here I say axis alignment very loosely because I think that what you're striving for here is that the concept embedding vectors just happen to be orthogonal to each other. There's no reason why an arbitrary basis should have that property. Like they could be arbitrarily non-orthogonal. So I think it's surprising that Llama chose to orthogonalize those vectors. But I think that the other models that you've been studying, they clearly don't form any sort of orthogonal basis. And maybe that's almost less surprising.
Yeah. So okay, maybe let me just throw out some vibes and see if this feels compelling. So okay, so one thing that you could imagine that is happening is that if you just look at the Llama training data, maybe it's the case that like most causally separable things are actually approximately statistically independent. Right. So like maybe it actually is the case that like, you know, French versus English and male versus female, right? If you have like a large enough corpus, those things are like pretty close to independent, right? That seems plausible, right? And so that seems like necessary as well to get the Llama structure, right? If that wasn't true, we would somehow expect the dependency structure to be baked into the geometry of the embeddings. Right? And well, maybe actually, right? It's not obvious, right? But the point is, even if we had that independence, right, by itself, that's not enough to give us like the orthogonality, because there's nothing in the objective which says like independent things should be mapped to orthogonal vectors, right? So like there's two gaps. There's the causal to statistical thing, right? And so it seems plausible that like those actually do happen to somewhat align in the training data. Right, but then there's also like a you know, even once you have a statistical structure, right, like what forces the statistical structure to be represented in the geometry of your embeddings, right? And like that second point is also a mystery, right? And so my guess, which is purely just a guess, is that what happens in Llama, right, is that there's actually some L2 regularization applied to the unembedding matrix, right? So like applied column-wise. And so guess is even too strong. A conjecture that one might have, right, is that really what is happening is like L2 regularization plus approximate independence causes things that are statistically independent to map to orthogonal vectors, right? Like that is a thing that could explain the structure, right?
Okay, so that really makes sense if the L2 regularization, then, you know, that picture you had, or the lack of identifiability of that, you know, you have this A inverse A. If in fact A inverse is A transpose, it's rotation matrix, then you do preserve those inner products. So that L2 regularization would do exactly, it's like in factor analysis with the Gaussian, you know, it's just up to rotation as opposed to like any arbitrary invertible matrix. So like that seems right.
Yeah, right. Yeah, exactly. So I mean, like minimally, like if you put on L2 regularization, right, then like that is a gamma thing, right? So at least you now have identifiability in your trading objective, right? But it's still a mystery why identifiability would correspond to independent structure, and a mystery why independent structure would correspond to causal structure, right? But it at least becomes plausible, right? Like there is some extra thing that is happening which like breaks the non-identifiability, right? And then you can something, it seems plausible that like this is what's explaining the Llama structure, right? But and then, you know, like I conjecture that this is a thing just because I don't know actually how Gemma was trained, right? And so it's possible Gemma just didn't have L2 regularization, and like that's the key thing, right? But again, I don't know that to be the case, right? It's just a guess. But like, you know, it's at least like there isn't a contradiction, right? Similarly, there might be something about like implicit bias of gradient descent, or something about how the unembeddings get initialized in the first place, right? You know, there's like all sorts of details where it's not like the way we train these models is not actually just an Oracle, you know, minimization problem. Yeah, and so I think like really the main takeaway that I want to convey though is like, even though Euclidean looks seductively close to correct, even in Llama 2, right, you get noticeable improvements by doing the whitening, right? And also the reason that Euclidean looks even remotely plausible is something idiosyncratic to Llama 2, right? Like it's not a thing you would generically expect from language models. And so you can't rely on Euclidean in general for the interpretation of LLMs, right? Because like we can have performant LLMs where like Euclidean has no privilege status. Cool. All right. Any other questions? Andre? Oh, sorry. Never mind. I saw my own mouse as a hand and got confused. Yeah, Burton?
Yeah, thanks, Victor. That was awesome. These are great papers, and I think they're really pointing in really, you know, important, fascinating directions. I'm curious to know, like, if your group's done other work, like in extending these ideas to like other tasks, right? Like not just last word or next word prediction, but like even just masked, you know, prediction. So like your right, like your embedding vectors would be embedding, you know, sentences that had maybe multiple words missing, and then you'd be predicting what, excuse me, one or more of those. And I'm asking that mainly because I'm now thinking about, you know, generalization to like even like other objectives, like and moving away from even language and going into like more unstructured things like images and like visual concepts and things like that. And just kind of curious to hear what you've done or what your thoughts are along those lines.
Yeah, great. So, you know, like we did do some stuff with stable diffusion, right?
Yeah.
And
So sorry. Yeah, I did.
But like,
Yeah. So I'm aware of that, and aware of how like you rely on, you know, Stein score and things like that.
yeah,
But that's not always going to necessarily be part of the objective. I mean,
yeah,
I mean, maybe
sure.
one could like interpret some of these objectives in that way, and maybe you've done that work. I don't know.
So I have not. I think it is a super interesting direction. As you're probably aware, I think like the work that I'm aware of, which feels most convincing to me along those directions, is from Jason, but I think not yet published. So you know, that my answer would be read Jason's unpublished work. But yeah, no. So I think we are still mostly thinking about just like these straightforward contrastive objectives because it is sort of like the easiest thing to analyze. But like, you know, I do agree, like sort of like loosening this up and like, you know, thinking about like patch structure or whatever seems very promising. And also like empirically, these like linear structures appear pretty universal. And so like you would expect that like some translation of like, oh, you need a causal inner product for the structure to really make sense. Like some analog of that should exist even in these other situations. But yeah, no, like basically we have not done anything more like, we haven't made more progress on that than what I just said. Yeah, and so.
Okay, cool. And that's a great endorsement of Jason's work. Thanks.